Hello students. So in the last module we were talking about the extraction of zinc, whereas in this module we will talk about aluminium. So the point is the extraction of aluminium important? For that we need to understand the uses of aluminium. Yes, aluminium is the most abundant metal found on the earth's crust, and the major application of aluminium comes in the packaging industry. That is used for making foils. Secondly, it is also used for making utensils and paints, and aluminium is also used for making alloys like durabilum, which is used for construction of aircrafts. So extraction of aluminium is definitely important. So the first thing that we need to talk about is the minerals and ores of aluminium. Aluminium in nature can exist in several forms. It can exist in nature in the form of a bauxite, which is an oxide form. It can be in the form of a cryolite, which is Na3Al(F)6. It can also be in the form of corundum, which is also an oxide form having a molecular formula Al2O3. It can also exist in nature in the form of a dispore, and finally it can also be in the form of a china clay. Now all the substances, wherever there is aluminium, we call it as a minerals of aluminium, but the ore of aluminium is bauxite. So aluminium is extracted profitably and cheaply purely from bauxite. So going to the second step, we will talk about the concentration, and as we know, concentration means removal of unwanted gangue particles. As we know, aluminium has to be extracted by a technique called as leaching, because leaching is purely used for aluminium, gold and silver, whereas aluminium can also be leached by several processes. For example, it can be leached by Bayer's process or Hall's process, or also it can be leached by Serpek's process. And please remember, Bayer's and Hall's process are used for red bauxite, where iron will act like a major impurity, whereas Serpek's process is used for white bauxite, where silica acts as a major impurity. So the concentration technique is done. Now the next thing that we need to talk about is the Hall's process in detail. As we know, the industrially preferred method is the Hall's process. So let us see in detail what is this Hall's process. As we know, bauxite contains lot of impurities. So in order to avoid these impurities, or in order to remove these impurities, we need to add a leaching agent. And the leaching agent in the Hall's process is sodium carbonate. So what will happen is, since we use carbonate, the first gas to come out is carbon dioxide. And this leaching agent will react with bauxite, and they will convert them into a sodium salt of bauxite, which is a water soluble compound. And this water soluble compound is called as sodium meta-aluminate. And then there is a lot of gangue particles or the impurities which are water insoluble. So this water soluble metal compound can be separated from the water insoluble gangue purely by a process called as filtration. So that's the first step. In the second step, we'd have to regenerate the leaching agent. So for that, we have to take sodium meta-aluminate and has to be treated with few molecules of water. As you can see, the leaching agent over here is sodium carbonate. That means we need carbon dioxide in the reactant. So the carbon dioxide gas which has been escaped has to be passed back into the reactant. Well, this will lead to the generation of the leaching agent, and we get a concentrated metal compound, which is the aluminium hydroxide, which is free of gangue or the free of impurity. Well, this aluminium hydroxide has been further heated so that they lose few molecules of water, leading to the formation of a dry powder called as alumina. Hence the name leaching of alumina from bauxite, and the process is a Hall's process, and the leaching agent is sodium carbonate. Now, since we are done with the concentration technique, now it is time for us to talk about extraction. As we know, extraction involves two steps. In the first step, we have to convert a metal compound into a metal oxide. But as you can see, alumina, it's already in the form of an oxide, hence we can avoid the first step. Going to the second one is converting a metal oxide into a free metal, which can be done by three methods, that is hydrometallurgy, pyrometallurgy and the electrometallurgy, and the method that we'll choose over here is electrometallurgy. So electrolysis of fused alumina will be done, and that electrometallurgical reduction of alumina is also called by a name Hall's and Herold's process. So now it is time for us to see in detail what is Hall's and Herold's process. So for that, let us understand the apparatus which is required. So the apparatus which is required looks like this. So first of all, we will have an electrolytic vessel which is usually made up of iron tank. And now it is time for us to talk about the electrodes. And the electrodes that we use, the cathode will be carbon, and the anode will also be a pure carbon that is in the form of a graphite. So anode and cathode both are done. Now it is time for us to talk about the electrolyte. There is a list of electrolyte that we need to put, which contains alumina, which is nearly 2 to 8%. The next thing is we need to add cryolite, which is 80 to 85%, and then there is a few few% of AlF3 and also CaF2 we need to add. Now the point is, why are we adding so many components? We are adding alumina because we are looking for aluminium. Secondly, we are adding cryolite because cryolite will lower the fusion point of alumina, and aluminium fluoride and calcium fluoride will help in the better conduction of electricity. So these are the components that we need to add. So now when you pass electricity, the following reactions are going to take place. The very first thing is, cryolite will first decompose to give you NaF, that is sodium fluoride, and AlF3. This AlF3 will further break down to give the corresponding ions, that is Al3 plus and 3F minus. Aluminium ion, which is a positively charged, will migrate towards the negatively charged electrode, that is cathode. But cathode is the electrode where reduction takes place, and reduction is gain of electrons. So Al3 plus will accept 3 electrons and they will form aluminium. So aluminium is obtained at the cathode, which can be easily removed from the drain plug, which is at the bottom. And now it is time for us to talk about the reactions occurring at anode. So fluoride ions will migrate towards anode, but anode is the electrode where oxidation takes place, and oxidation is loss of electrons. So F minus will lose an electron and they will form F, but we don't have anything called as F, but we have F2. So balance the reaction by putting fluorine. Once fluorine is liberated at anode, this fluorine will react with alumina and they will lead to the formation of the same compound, that is AlF3. So the same reaction will continue, and more and more aluminium can be obtained from the drain plug. But the point that we need to notice over here is oxygen is liberated at anode, and anode is made up of carbon, that is graphite. So what can happen is, this oxygen can react with the carbon and they may lead to the formation of carbon monoxide and carbon dioxide according to the following reaction. So C plus O2 can give us carbon monoxide, which is a poisonous gas which can react with excess of oxygen and they can lead to the formation of carbon dioxide. So all that we need to remember in the Halls and Herold's process is, the molten pure aluminium is obtained at the bottom, and for every 1 kg of aluminium which has been produced over here, nearly 0.5 kilogram of carbon is burnt away in the form of a carbon dioxide. So that is the Halls and Herold's process, which is the electrometallurgical reduction of aluminium. Now the aluminium which is obtained, the next thing we need to do is refine them, and the method that we choose is called as Hoops electrolytic process, which basically consists of 3 fused layers. The bottom layer is made up of impure aluminium which can act like anode, and the middle layer will act like an electrolyte, which is a mixture of Na3AlF6, which is cryolite, and BaF2, barium fluoride, and the top layer, which is a pure aluminium which can act like cathode. Now when you conduct electricity, the aluminium from the bottom layer will migrate towards the top layer, leaving the impurities at the bottom. So this way we can obtain pure aluminium.